How to break Einstein's speed limit. Lecture 2. Two-particle bound states by Eugene Stefanovich. Here is the outline. First, we will recall Dirac's theory of relativistic interactions. Strictly speaking, we have to work with quantum mechanics in a two-particle Hilbert space. But we will simplify our task by switching to the classical approximation where commutators are replaced by Poisson brackets. I will remind you about the instant form of Dirac dynamics, and we will discuss an ingenious interaction model proposed by Bakamian and Thomas. The second part of the lecture will focus on a numerical solution of the dynamical problem. First, we'll obtain trajectories of interacting particles in the rest frame. Then we'll transform them to the moving frame and realize that at some portion of trajectories, particles move faster than light. Finally, we will establish that this does not constitute any violation of causality. Here is how Wigner-Dirac theory approaches a system of two interacting particles. We have H1, the Hilbert space of the first particle. H2 is the Hilbert space of the second particle. And we construct the Hilbert space of the two-particle system by forming the tensor product of H1 and H2. By construction, in the tensor product space, we have all operators of observables related to the first particle and all observables of the second particle. These operators commute with each other. Next step, we have to build a unitary representation of the Poincaré group in this Hilbert space. A simpler but equivalent task is to find three Hermitian operators that satisfy commutation relations of the Poincaré-Lie algebra. This task can be further simplified if we switch to the classical limit. From our first lecture, we know that it's not a bad approximation to think that quantum wave packets remain localized and move along classical trajectories. Then, instead of quantum commutators, we can use Poisson brackets of classical mechanics. And in terms of Poisson brackets, the Poincaré commutators have the following form. As usual, we can start building our theory from the simplest non-interacting case. Then the desired generators are constructed simply as sums of one-particle observables. It's very easy to prove that the Poincaré commutators are satisfied in this case. So relativistic invariance is guaranteed. We can define other observables of the non-interacting system, such as the total mass and the center of mass position. The next question is how to introduce interaction in this picture. It was answered by Paul Dirac in his important paper. In particular, he suggested the so-called instant form of dynamics in which interaction potentials are added to the generators of boost and time translations. It should be possible to select these potentials in such a way that the Poincaré commutators remain unaffected. As we know, this is the condition for the interacting theory to be relativistically invariant. We discussed Dirac theory in one of our previous lectures. And we noted there that the construction of relativistic interaction potentials is a very non-trivial task. Here I would like to discuss one famous analytical solution of this problem, which belongs to Bakamian and Thomas. It was described in their paper published in 1953. Here is the idea. In our non-interacting representation, we have external observables of our two-particle system, the center of mass position and the total momentum. These are conjugate variables as their Poisson bracket is equal to 1. Let us now define internal or relative observables. Here is the relative momentum pi. In the non-relativistic world, it would be simply a difference of particle momenta divided by 2. In the relativistic case, we have an additional term. Then there is the relative position ρ. Again, it's more complicated than the simple non-relativistic difference R1 minus R2. It is justified to call these variables relative momentum and position because their Poisson bracket is equal to 1. And Poisson brackets between relative and external observables are all equal to 0. Now, Bakamian and Thomas suggested to build an interacting theory as follows. According to them, it's sufficient to form the interacting mass operator by simply adding to m naught any real function of the internal variables u of ρ and pi. Then the three generators of the interacting representation are constructed as follows. By definition, the instant form generator of space translations is interaction-free. The Hamiltonian is given by the usual square root, where the mass operator was modified by the potential u. And the boost operator is given by the usual formula, with the only difference that the Hamiltonian factor contains interaction. Bakamian and Thomas proved that this construction satisfies all requirements of relativistic theory. In order to apply this theory in practice, one can simply choose an arbitrary potential u and solve Hamilton's equations of motion with this potential. This is what we did in our 2010 paper. In our example, we chose a screened Coulomb-like potential, and we placed the two particles in the center of this potential and gave them very high opposite velocities. As the potential was attractive, the particles, red and blue, started to oscillate around the common center of mass. Next, we look at these trajectories from the point of view of a moving observer. We use the interacting boost generator to make this transformation. As expected, we saw that the period of oscillations has increased more than 8-fold. This is a famous relativistic time dilation. But what's more interesting, we found that some portions of particle trajectories now have velocities that exceed the speed of light. There was no superluminality if the original trajectories were transformed by Lorentz formulas of special relativity. What is going on here? It appears that we managed to build a fully relativistic theory which violates the most fundamental law of special relativity, the ban on superluminal velocities. Isn't it a paradox? According to special relativity, the presence of superluminal motion means that for some observers, the particle appears as moving backward in time, thus violating causality. But the whole point of my lectures is that Lorentz formulas cannot be used to make transformations to the moving frame. If we want to maintain a representation of the Poincare group, our boost transformation should be performed with the help of the interacting boost generator K. For example, by solving these quote-unquote equations of motion in the rapidity space. But these transformations are different from Lorentz formulas. Properly transformed trajectories remain perfectly causal in all reference frames, even though in some frames velocities may exceed the speed of light. What regards Lorentz transformations of special relativity, they are okay for non-interacting particles, but they are not applicable to the interacting case. Thank you.